So in the first chapter of this course, we kind of looked at, among other things, the age of our universe, going back to what is proverbially called the Big Bang. So we said that that's about 13 billion years ago was basically our universe's time and space began unfolding. The fabric of space-time is kind of how I think of it. So that's about 13 billion years ago, about. So now how old is our solar system? Well, we can study our solar system. We can study the planets in our solar system and the sun differently, actually aging it a little bit differently than we need to study aging the universe. But when we go to date the planets, get a fix on the age of the planets, one of the things that we rely on are these leftovers, these crumblies, I said. And if a meteoroid or an asteroid falls through the Earth's surface and some of it's ready to, some of it successfully gets to the Earth's atmosphere without burning up, if you can pick it up, we call that a meteorite. Okay, so meteorites are kind of space rocks then, right? Meteorites are space rocks. And so we've studied meteorites, that kind of the leftovers of the formation of our solar system. And one of the ways we've studied meteorites is to look at the different elements present. So now we're kind of looking at specific atoms. And we look at, remember we talked about isotopes, that certain elements can actually have more or fewer neutrons in their nuclei. So if you know what you're looking for, you can use the atoms and specifically isotopic information about the elements or atoms to understand dating. So here's how this works. Certain elements will decay over time. They're unstable. And you know, well, how unstable are they? Well, we talk about these things called half-lives, and it means that basically half of that material will decay over a certain number of maybe billions of years. So here's the example I've got for you. Potassium, isotope number 40, will decay into another element. Argon, also isotope or mass number 40. So of course potassium and argon are two different elements. So we see potassium decreasing over time, and we see argon increasing over time. Now, this sort of rate we call radioactive decay. So the decay part is potassium is decaying into argon. The mechanism by which these atoms will decay is very well known, and we can anticipate the decay rate. So it has a half-life of, this process has a half-life of 1.25 billion with a B years. Okay, so so about half of it will be used up in 1.25 billion years. Then half of that half will be used up in another 1.25 or 2.5 billion years. And then you add on another half-life of 1.25 billion years and you get up to 3.75 billion years. See how that works? All the time the potassium is decaying, the argon is increasing. So basically then what you do is you sample your rock, your meteorite, and you see how much argon has been formed and how much potassium has been decayed. And you can use half-life information. It's, you know, I don't think that the calculation is that complicated, but using the relative amounts that are remaining of potassium 40 and argon 40, you can know how old that rock is. Okay, so there you go. So half-life is the time it takes for half of that material to go ahead and decay into, in this case, argon 40. All right, so there are different types of meteorites out there. Remember, a meteorite is a meteoroid, as it was in outer space, but it fell through the Earth's atmosphere, and some of it survived, and you pick it up in the form of a meteorite. So basically, Some meteorites have been dated going back to as old as 4.6 billion years old. So these are the crumblies, all right, of our solar system. So just to kind of throw some more dates at you, so that was 4.6 billion with a B years old. Well, visiting the moon, we did go ahead and take a few moon rocks and bring them back to Earth to study. And we have dated those, or scientists have dated those at being 4.4 billion years old. So that's a little bit younger than the 4.6, isn't it? Oldest meteorites are dated at 4.55 or 4.6 billion years old. And so what we now believe is that the planets probably formed, were basically done with their accretion about 4.5 to 4.6 billion years ago. And so when the accretion stopped, one of the ways I think of it as it stopped because the sun turned on. Remember in a previous lecture, I talked about when the sun turned on, it created this solar wind that's been going ever since. So about 4.5, 4.6 billion years ago, the sun began shining.